All right, so we're going to be talking about tolerances today for 7.3. So let me make this big. I'm going to switch this to the other screen, and here we go. So tolerances. Um, so if we're looking here, uh, what we've got is, what is a tolerance? And that's a variation that you can't avoid. So it's impossible to make two things exactly the same, but we want to get as close as we can. This is like when we did the project with the blocks and we were measuring all the blocks to see what was acceptable. We were setting a tolerance based on a standard deviation. So we were trying to see like what's the acceptable range in these parts. We ordered them all so they were the same, but they don't come to us that way. So we do something called a tolerance, which tells us what degree of variation is acceptable. So they're used in production drawings to let the control and manufacturing know when they're doing their samples off the line what's acceptable for this part. So this is big when you're doing mating assemblies, like two things that have to go together. This is a big advantage with interchangeable parts when you can use them, because without tolerances, copies of individual parts may vary significantly, and then we wouldn't be able to use them to fit parts together. So, large tolerances may affect the functionality of a part, whereas small tolerances will affect the cost of the part. And we're going to get through that too. So, without tolerances, copies of individual parts could vary significantly. And we've got different families. We've got ANSI, AMPSI, the American National Standards Institute, um, where each dimension shall have a tolerance, except those dimensions specifically identified as reference, maximum, minimum, or stock. The tolerance may be applied directly to the dimension, etc. So, if we're looking at tolerances, we've got different ways of doing it. And as far as this is going, is like I said, it's an acceptable amount of variation. Now, there are three basic tolerances that occur in our drawings, and they're all listed here. We have the limit dimension, which sets an upper and lower limit. We have the bilateral tolerances, which also set an upper and lower limit. Oops, sorry. Mouse move around. It's on the wrong screen of the mouse. And we have the unilateral, which has only one direction where we allow variance. As you see here, it can increase but not decrease. So limit dimensions. So when we're looking at limit dimensions, this is how we should look at them. This is our limit dimension. It provides an upper and lower limit for that dimension. So as long as when you manufacture this part and you put your caliper in here to measure, it's between these numbers, you're good to go. Any size between is allowed, but if it's lower, it's not good to go. Bilateral means you basically got to do the math to figure out what the limit dimension is. It gives you an acceptable variance here. So you have to figure out what the upper and lower limit is, and it's this dimension plus this and this dimension minus this gives you your range of acceptable dimensions. I want to see if it's going to give me that here. So it didn't do the math. So like in this case, just get my pen out here. In this case, the acceptable variance would be 1.55 and 1.45. Anything within this range is acceptable according to this dimension. So that's very important to know. Continuing on, and then you got unilateral, which you're going to create basically a limit dimension looking at this again. As basically says, you got your 0.5 as the lower limit, which is acceptable, but you can go all the way up to 0.504. Like anything within this range is acceptable. And that is what that is saying. So those are the three types of dimensions. And then we've got to identify them. So like if we're identifying this, and in class I would have you identify this, but since you're not here, let's just go through. We got our unilateral, because it can only change in one direction. We've got our bilateral, which means it can change both upper and lower, and then we've got our limit, which gives us what the actual range is right from the get-go. And then we have specified dimensions. So like this is a specified dimension. Every dimension has that. That's what you're used to doing. And then after you have your specified dimension, you have your limits. So limits are based on maximum and minimum. So you have an upper limit and a lower limit, like I did for this earlier, where to figure out your upper limit, you have to take what the bilateral dimension is giving you, and you figure out your upper limit. And you also take what your bilateral limit's giving you, and you subtract it to find your lower limit. So this is very important stuff. So the total tolerance for this, which is the maximum variance you have, is your tolerance, is 0.1. Like this has a tolerance of 0.1 from the specified dimension. So as long as you go up and down, based on that, it gives you a tolerance of 0.1. So that's like our degree we're using in there. So calculating the tolerance, you got the 0.5 this way, 0.5 that way, you add them together, or you subtract this from this, and that gives you your tolerance. So tolerance is the total range based on what your bilateral dimensions are. And then there's something called general tolerances. So if you're not specifying individual dimensions on your drawing, sometimes you use a general tolerance chart, which is right here, where you have your dimensions. And it's like if I have a dimension that would say like 1.1, this would be its tolerance. But if I had a dimension that was 1.11, this would be its tolerance. And if I had a dimension that was like 1.123, this would be its tolerance. And it's usually just put somewhere on your drawing, and it specifies your tolerances. So like as we see in this drawing down here, we have our tolerance chart, and for a dimension like this would be our tolerances because it's got 2 decimal points. So our tolerance would be plus or minus. Let's see if it's going to do the math for this somewhere. So here we go. The upper limit we're adding, and the lower limit we're adding, and then the total tolerance is the upper minus the lower, which gives you this. So that is very good. So if things are out of tolerance and they're not within their specified limits, these parts get rejected. Just like when we were measuring the blocks, we rejected some of the blocks because they were too far out of the standard deviation. They were out of our tolerance set by the standard deviation. And then we've got all sorts of different fits. This is where it gets a little more confusing. So we've got clearance fits. This means this part, which would be considered the male part, is going to fit into the female part with no problem. It's going to clear. Nothing's going to hit anything based on this. And how do we know that? Well, we'll get back to it. We've got interference fit, where the male part's going to hit the female part on the edges, and there's going to be interference. And we base this on the maximum material condition. So the largest amount of material, which is different for an external or internal part. So, and then there's the least material condition. So an allowance is not the tolerance. This is the maximum material condition of the internal feature minus the maximum material condition of the external feature. This is the allowance. And if we have a positive allowance, that means that we have a clearance fit. So if we look at this, our maximum material condition of our internal feature, get my pen out. So of my internal feature, this is the maximum amount of material, because a smaller number here means the hole is smaller. And since the hole is smaller, it means there's more physical material on both sides. So that means that there's more material here on an internal feature because the hole, you want it to be smaller to get the maximum material condition. So that's very important. So that's where we're getting this number. That's why it's the maximum material condition, because this material is larger if we get the lower tolerance as opposed to the higher, because this would mean the hole was bigger, which means there's less material. The maximum material condition on our external feature is the larger number, because that means the diameter here is larger, and since this is a solid object, having a larger diameter would mean that there is more material than this. To figure out if there is an allowance, you would take the maximum material condition of the internal feature and subtract it from the maximum material condition of the external feature. And if the number is positive, you have a clearance fit. All right. So that is how we get the clearance fit. And I just did that all with my marker, and that's fine. So you see here, on the second one, which it did all this stuff for me, we do the same thing. We took the maximum material condition, the internal. We took the maximum material of the external. We subtracted them, and we got a negative number. If you get a negative number, you have an interference fit. So that is an interference fit. So just to go back, there was a third kind of fit here I didn't talk about, and this is a transition fit. And this occurs when two mating parts sometimes have a clearance and sometimes have an interference. I'm going to tell you, I've never seen this on the test where you get a transition fit. But basically, this would be like, say, if we looked at all of this, and sometimes, like if we took the maximum materials and subtracted them and it gave us an allowance, that's good. That's a clearance fit. But then if we looked at the opposite end, the least, and we subtracted them and we got an interference fit, or vice versa, some way, that'd be a transition. Whereas if we subtracted the opposite numbers, and one way it's an allowance and the other way it's an interference, that'd be a transition. I mean, sometimes it's a clearance, but sometimes it's an interference. That's a transition fit. Pretty much you're going to see in this course we're typically dealing with clearance or interference, not transition, but it doesn't mean it can't happen. Okay, so this is the lesson on tolerances. There's going to be a couple assignments on this. The first of which, if we can go back here, if we look at this, the first of which is going to be answering the questions based on this rocker arm that I'm going to have several questions on another sheet. And I'll probably do a video on that to help you guys out, but this is all your lesson for today, so good luck with it.